So we're up to chapter 20, podcast number 4, and this is dealing with the effect on Gibbs free energy change, right, when we change temperature, pressure, and or amounts. So we are now going to see what happens when we are not at standard conditions for a Gibbs free energy change, and does that affect whether we have a spontaneous reaction or not. All right, if we go and look at the Gibbs-Helmholtz equation, right? Again, this is a refresher from our previous podcast, but it has delta G is equal to delta H minus T delta S, right? So Gibbs has a high dependency upon the temperature, right? However, delta H and or delta S don't have a very big dependency upon the temperature, right? They change very slightly, yeah, like we saw that our entropy is going to increase as the temperature increases because it's becoming more and more random, right? And enthalpy also is going to increase as we increase the temperature as well. And so those things, though, they increase in the same direction as each other. And because the Gibbs-Helmholtz equation is delta G is equal to delta H minus T delta S, right? What that means then is that, like, we have the delta H and the minus T delta S. If they're both increased by an increase in temperature, well, they're going to cancel each other out because of that minus sign in the Gibbs-Helmholtz equation, right? So they don't really factor in, right? But delta G is really dependent upon our temperature. And we can look at this by actually calculating a whole bunch of Gibbs free energies at different temperatures. And when we do that, what we're going to get is we are going to get a line, right? And that line is going to have a slope of minus delta S, and the y-intercept is going to be 0 Kelvin, right? Or sorry, the y-intercept at 0 Kelvin is our enthalpy change. Now, I don't bring up linear relationships all that often, even though there's a whole bunch of them in Chem 2, but this one is important, and I would say that knowing these couple pieces of information will probably come in handy on exams, especially on those conceptual questions. That I love to ask. All right, when you got those conceptual questions, I might ask, okay, is this reaction going to have, right, if from one temperature to another temperature, are we going to have an increase in entropy or a decrease in entropy? Well, you can find that from looking at the slope. Or I might have this, graph where I'm like, oh, okay, well, I want you to tell me what is the enthalpy change in this? And all you have to do is look at, all right, where is the y-intercept then? Right? And that's what we're going to see on the next slide is we're going to see this visually as well. So let's take a look here at an actual graph where we're graphing our Gibbs free energy, standard Gibbs free energy changes at different temperatures, right? And this one is showing it from 0 Kelvin all the way up to 1200 Kelvin. All right, the reason that I show this is that there is a lot of information that can be gleaned from this, right? Our first piece of information, number 1, y-intercept, right, at 0 Kelvin. All right, y-intercept at 0 Kelvin is right there, that black dot over there. All right, that is at 98.8 kilojoules, and that is our delta H. All right, number 2 piece of information that we can glean from this is our slope goes down. This is a negative slope. All right, so thus the negative of a negative delta S means that whatever this is has a positive delta S, right? Negative slope is that it's going right down from left to right, right? And remember, right, that our slope is the negative delta S, so thus we have to have a positive delta S overall. Right, the last piece of information that we can glean from this thing, another thing, is number 3. All right, notice where we cross the delta G of 0. And remember, delta G is equal to 0, right, at equilibria. All right, that's somewhere here, right, around, say, 650 Kelvin. I'm just, kind of eyeballing it there. All right, well, notice when we are all right, so notice that over here, right, in this region over here, our delta G is less than 0. Over here, our delta G is greater than 0. So this means that at temperatures greater than, like the 650 Kelvin, spontaneous, at temperatures less than 650 Kelvin, non-spontaneous reaction. So see, we can get a lot of information out of just this one figure that we see here. All right, so, right, we've seen that, right, by changing the temperature, right, on our previous slide, that, at certain temperatures we could have a spontaneous reaction, and at other temperatures it was non-spontaneous, right? Now, so we can make other changes to our system or to our reaction, right? We can change the temperature, but we can also change things like pressure and concentration. And so when we're not at standard conditions, when we change the pressure from 1 atmosphere of all of our gases, or when we change the concentration of all of our aqueous solutions to be not 1 molar, that can also affect our spontaneity. We're going to see each 3 of these in due time. First, we're going to go a little bit more in depth on changing the temperature, just to see how that's going to change our spontaneity. And then we're going to look at what happens when we change pressures and concentrations as well. So we have learned that when we have a negative enthalpy change, it is likely to be spontaneous. When we have a positive entropy change, it is likely to be spontaneous, right? But there are 4 possibilities when it comes to these. I could have a negative enthalpy and a positive entropy, right? Like the top one. I could have a positive enthalpy and a negative entropy, which is the second one. I could have them both be negative, or like the very bottom one, I could have them both be positive. All right, so I'm going to show examples of the very top one in black and the bottom one in green. Right, so a reaction for which an enthalpy change is negative and an entropy change is positive is spontaneous at all temperatures. Okay, let's see why that is by looking at our Gibbs-Helmholtz equation. All right, delta G is equal to delta H minus T delta S. Okay, I don't have any numbers, but what if I said that, okay, my delta G is equal to, all right, an enthalpy that is less than 0, so some value that is negative. All right, I'm going to take a negative. I'm going to subtract off my temperature. That temperature is going to be in Kelvin. Kelvin has to be positive, right? It's an absolute scale. Temperatures in Kelvin are always positive. All right, times an entropy that has to be positive from the statement up there, right? It's greater than 0. If you take any number that is negative and you subtract off minus a positive value, you're going to end up with a negative answer. So you'd end up with a negative delta G, which means that it's going to be spontaneous no matter what those values are. All right, the bottom one, right, says that we have a reaction for which our delta H is greater than 0 and our delta S is also greater than 0. All right, so we've got our delta G is equal to, all right, a positive delta H minus, all right, temperature is still positive because it's in Kelvin, and our delta S is positive because it is said so, right? It's greater than 0. You have a positive minus a positive. All right, so it depends on how large, right, these are, but basically, like, as I increase the temperature, right, as I increase the temperature there, right, then that whole factor becomes larger and larger, right? And so it's more and more likely, right, the bigger and bigger that gets, the more likely it is for the overall thing to become negative. So this is spontaneous at high temperatures, and it's going to be non-spontaneous at lower temperatures. All right, so make sure you understand these as well. So we have learned that, depending on the delta H and the delta S of a reaction, if they're both positive or they're both negative, then we can actually have reactions that will change spontaneity from being spontaneous to non-spontaneous at a specific temperature. Now, it might be as you increase the temperature, or it might be as you decrease the temperature, depending on those values, right? So remember, you've got to go back and look those over. But, right, where they change from being spontaneous to non-spontaneous, right? Spontaneous reactions are where we have a negative delta G. Non-spontaneous reactions are where we have a positive delta G. So where they're going to change is where we have a Gibbs free energy change at delta G of 0. So if we want to calculate the temperature when we have a change in spontaneity, right, delta G is equal to delta H minus T delta S, or 0 is equal to delta H minus T delta S, or that T is going to be equal to delta H over delta S, which is that equation right there, right? All I did was just do some algebra, plugging stuff in. And so once we know that, then, right, that'll give us the temperature at which we are going to change. Now, it doesn't tell us whether we're going to be spontaneous above or below that temperature. That we have to get from the signs of our enthalpy and our entropy. But it does tell us what temperature we do get that change to occur. So sample problem 20-5 says for the reaction of some 10,4 oxide plus 2 carbon oxides, we're going to produce 2 carbon dioxides and metal tin. It wants us to calculate the temperature when our Gibbs free energy change is 0, right? So this is also calculating the temperature at which, right, our spontaneity changes from spontaneous to non-spontaneous. So first off, we need to calculate both our delta H and our delta S, right? Our enthalpy and our entropies doing products minus reactants. Again, these values can be looked up, right? And in this case, they'd be given to you on an exam, but they can be looked up in a table in the back of your book or whatever we're doing there. And so what we're going to do is we're going to do our products minus reactants, just like we would for any of these. Again, in order to save time, I'm not going to work through doing all of the math to do our products minus reactants for everything. Right? But we can see that our delta H is going to be equal to, in this case, 14.7 kilojoules. All right, and our delta S is going to be equal to 31.3 joules per Kelvin. Okay, we're going to end up plugging these into the same equation though. So remember, right, we need our kilojoules and our joules to agree with each other, right? So if they don't agree with each other, then we can't work this problem correctly. We're going to end up with the wrong answer. So I'm going to go ahead and convert the delta S into kilojoules. You could convert your delta H into joules and it'll work perfectly fine, but I'm just going to do it this way, and I'm dividing by 1,000, so I get 0.0313 kilojoules per Kelvin. All right, now we can work on the second part of the problem, where we're going to set our delta G is equal to 0 and solve for T, which we'll do on the next slide. So again, if we set our delta G is equal to 0, then we're going to, 0 is equal to delta H minus T delta S, or that T is equal to delta H over our delta S. So now we can plug in our temperature. In this case is our 14.7 kilojoules divided by our delta S, which was, right, in the same units, 0.0313 kilojoules per Kelvin. So our kilojoules are going to cancel each other out, and we're going to be left with 470 Kelvin, or 197 degrees Celsius. If it asked us to put it in Celsius, we would do that conversion. It didn't specify. I don't believe in the problem, so I can just keep it in the Kelvin, 470 degrees Kelvin, and that's our final answer there for that problem. So again, when you have a problem like this, or during a phase change, we're going to work the exact same way. So either whenever it asks for when does this change from spontaneous to non-spontaneous, or when is there a phase change, we can always set our delta G is equal to 0. Well, we've seen the relationship between temperature and spontaneity there by looking at, at what temperature can we go from something being spontaneous to non-spontaneous if delta H, our enthalpy change, and delta S, our entropy change, are both either negative or positive that can affect it. All right, well, we can also have changes to our spontaneity when pressure and concentration are not at standard conditions. When they are not at standard conditions, right, notice that our delta G is equal to delta G naught plus RT ln of Q. All right, so, right, number one, there's no not symbol, right? So that means that we are not at standard conditions. And Q, this is not a K value. Which means that we're not at equilibria. So we can use this equation right? Remembering back that Q is the same thing as an equilibria constant, products divided by reactants raised to their powers, except that we don't have to be at equilibrium. All right, to use this equation, right, remember temperature has got to be in Kelvin. Please, as you're going through your next exam, do not forget to put your temperatures in Kelvin, right? It's a simple mistake that can get you a lot of points off if you don't do that, especially in this chapter. All right, R has to be in kilojoules per Kelvin, right? And so that is 0.0083145 kilojoules per Kelvin, right? And that is also 8.3145 times 10 to the minus third kilojoules per Kelvin. Right, either way you want to write that thing, just make sure that it's in those units, right? Because our delta G naught is going to be in kilojoules, and so we want to make sure that our R is also in kilojoules. Our temperature is in Kelvin, so our R needs to be in Kelvin. All right, and so our Q is the same reaction quotient that we've dealt with all semester long. We brought it up starting in chapter 17. Again, equilibria is not going away. Our reaction quotient isn't going away either. And that brings me to the end of this podcast, where in the next podcast, we're going to go way more in depth on the reaction quotient, calculating it again, and seeing how that actually is going to drive our reactions, whether they become more products or more reactants by looking that over. See you next time.